Okay, so in this video, as I mentioned before, we're going to take the two types of circuits we've spoken about, a resistor-only circuit and a capacitor-only circuit, and we're going to combine it into a single circuit. There are real-world applications for this, okay? So RC circuits show up as flashes in cameras, right? You can't just keep taking the picture, right, and the flash will go pop, pop, pop. Right? It takes a little bit of time. If you watch actually like the nice cameras a photographer looks, it says it's ready, then it takes the picture, looks, takes the picture because it has to charge and then discharge. Okay, and that's what we're going to do here. Another real world application is the circuit that contains the windshield wipers on cars. Windshield wipers, not windshields, right? So this is the same deal, right? As they go back, and this is where we're talking about the intermittent one, not the ones that are just going constantly, but the ones like you turn it on and then it comes back, right? Because it's the same thing. Once it makes its pass, it stops, charges, discharges, charging, discharging, charging, discharging, right? And so you change the dial to tell you how much time you want really or how much charge you want to sit onto it, and for it to actually kind of discharge, right? So a resistor circuit has a steady current, okay? And by adding a capacitor and a switch, we can make a circuit in which the current varies with time as the capacitor charges and discharges. Circuits with resistors and capacitors are called RC circuits. And we're going to talk about two other circuits later, an LC circuit and an LR circuit. L is an inductor. That's something completely different, okay? Now what happens is a capacitor can store charge, right? And a resistor placed in series with it can control the rate at which it charges or discharges, right? And so basically we're going to have like capacitor, and it's going to look, a basic one will look something like that. Remember, this is your capacitor, this is your resistor, this is your battery. Okay, so the battery is going to send a voltage out, right? A current out. It's going to use it. It's going to store the charge in here. Then after some time, it's going to be ready for this resistor to use it to discharge that capacitor. Okay, so this produces a characteristic time dependence that turns out to be exponential. And the crucial parameter that describes the time dependence is called the time constant. Okay, and so the time constant, which is given the symbol tau, is just simply the resistor times the capacitor. And so the greater the time constant, the longer it takes for the capacitor to fully charge. Okay. Now, when a capacitor of capacitance C is in series with a battery of voltage V and a resistor resistance R, the voltage drops must be, right? So the voltage drop has to be Q over C minus IR. Okay. And Q over C, meaning coming from the equation V equals CV, or Q equals CV, and IR coming from V equals IR, right? So what we did for the first one is we solved it for V, and then we solved it for IR, right? Or we just plugged in for IR. But we know if we do a little bit of kind of, algebra here, which leads us to our differential, we say 1 over C times Q minus R dQ dt, right? Because I is dQ dt, and that gives us our, so substituting I equals dQ dt, that would give us our exponential relationship. Now, I can do a video, or I'll do a video about how to solve this, but here are the equations for the charging and discharging. So the charge when discharging is simply Q0 e to the negative t over RC, or tau. For charging, it's 1 minus e to the negative t over RC, right? Or RC, remember RC is tau. The current will be I equals IO negative T over RC. And so the current will, the equation for the current is also going to be the same for that, for the charging piece. And then for the voltage, the voltage is going to be VO1 minus E to the negative T over RC. But remember, sometimes in the equation you'll see the tau written in there, and tau is just RC. Okay. So those are the equations. I do not believe that these are not given to you. I believe these are not given to you on the AP Physics C chart, so you'll want to memorize those. But you may be asked to derive those, okay, which will be a separate video. So here's an example. It says, given the following RC circuit, calculate the following. A, the time constant. B, the voltage across the capacitor at exactly 0.7 time constants. The voltage across the capacitor at 1 time constant. The time to fully charge the capacitor from supply, and the voltage across the capacitor after 100 seconds. Okay, and so let's go and find the time constant. All right, we know it's going to be tau equals RC. So all we're going to do is 47 times 10 to the 3, right, because it says kilo ohms. And then we're going to do 1,000 times 10 to the negative 6 farads. So 47, so it's going to give us 47 seconds, right? Now, this is not how long it takes to fully charge or whatever. This just tells us that this is the time constant, right? This is that time dependence piece. So in any of those equations above, our R times C will be 47. All right. B, right? The voltage across the capacitor is exactly 0.7 time constant. So our T is going to be 0.7 and do 0.7 times tau. So it's going to be 0.7 times 47. And so they're talking about after how many seconds? 32.9 seconds is what we're looking for part B. And we're looking for the voltage. So we're going to do V equals V0 times 1 minus E to the negative T over 47. And so our initial voltage is 5. 1 minus negative 30, E to the negative 32.9 divided by 47. And so that tells us after 32.9 seconds, it's going to be charged, it's going to have a voltage of 2.52. Part C, the voltage across the capacitor at 1 time constant. So, right, again, this doesn't mean that it's fully charged. Okay, so we're going to use the same equation. Okay, so we're going to do 5 times 1 minus negative E to the negative 47 over 47. And that's going to give us a voltage of 33.16. And so the way you think about this, at this point in time, after 1 time constant, it's about 63.2% charged. Okay, so it's not fully charged after 1 time constant, but it's working to get there. And they say for a capacitor to be fully charged, it's approximately 5 time constants. And that gets you to about 99.3% charge. And then to a capacitor that is fully charged. And so part D says the time to get to full charge, and so we can use that fact, right? So we're going to do 5 time constants is fully charged, so it's 5 times 47, which is going to be 235 seconds. Okay, and we can figure out, you know, how much voltage after 2 and what percentage and everything. Okay, and part E, the voltage across the capacitor after 100 seconds. So basically, we're just going to plug in 100 for our T. So V equals V0 times 1 minus E to negative T over 47. Again, we're using the 1 minus because this is a charging piece, right? So if we were discharging it, then we would use the other column up there. We would just use the E to the negative T over RC. So we say 5 times 1 minus E to the negative 100 over 47. And I actually I forgot to calculate this one. So e to the negative 100 divided by 47. And so we're at 4.4 volts, right? And so at 100 seconds, which is about half of the full time charge, we're at 88% charge, right? And if you did the quick 1 minus negative e to the 2, so if I did the calculation using the 5 time constants, right, the voltage for this would be 4.97 volts. Even though we're not quite to the 5 volts, we're at 99.3 or approximately 99.3%, 99.4% charged. Okay. So again, I mean, you're breaking down the circuit, right? And just really determining charging versus discharging of the RC circuit. So that ends chapter 3 or unit 3 in E&M. The next unit is where we'll start talking about magnetism, and then the last unit is electromagnetism.